Good. Hi everyone, and welcome to PyG webinar about distributed training of GNNs. We are very excited to have you all here and turn up in huge numbers. And we are also very excited to present to you the latest additions of functionality and a latest major release of the PyG graph neural network framework. And we are especially excited and for the collaboration we are having with Intel, who is a major contributor to this release and especially to the distributed training of GNNs framework that we are going to discuss. With all this, you can now scale PyG models much larger than what was possible before. So agenda for today. First, my name is Jure Leskovec. I'm Chief Scientist and co-founder at Kumo AI. And I'll first give a brief introduction about how are we thinking about graph neural networks at Kumo. Then Matthias, who's the founder of PyG and a founding engineer at Kumo, is going to present the release notes for PyG 2.5. And then our friends from Intel, Kinga and Jakub, are actually going to talk about the distributed training and the way it's implemented and done in PyG. And we are also going to show you a live demo so that you are able to kind of get your hands on and get a sense about this. So PyG, or pytorch-geometric, is the most widely used graph machine learning library out there. And it implements the latest and the greatest research, infrastructure, architectures, and so on. We have a very thriving community of over 470 open source contributors, nearing 20,000 stars on GitHub. We get about 200,000 monthly downloads, and we have a very active Slack community of around 6,000 people. Most importantly, over 3,000 research papers have used PyG to develop new architectures and further the graph neural network research. And also, we are very excited for the partnerships we have with Intel and NVIDIA, who are actively contributing to the framework and making sure that it's supported and runs well on the latest hardware. GNNs have proven to be extremely effective at all kinds of prediction tasks. At Pinterest, we pioneered this area by developing the first industry-grade platform. It took us 3 years to build with a huge investment in engineering, but also to great success. Our metrics increased by 30 to 50% at that time. Other companies were able to replicate this success. Uber and Amazon are reporting great gains in their core use cases from graph neural networks. And perhaps most interestingly, it's actually the case of LinkedIn. They just published their paper about their internal PyG-based graph neural network platform. It took them just 6 years to build it, but they see amazing gains across all kinds of machine learning AI use cases at LinkedIn. So from job fit engagement recommendations to job applies to weekly active users, number of sessions, things like that. The paper is truly impressive. It's a huge paper, 23 authors, and was posted on Archive about 2 weeks ago. I really encourage everyone to take a look at it. It's really impressive to see how graph neural networks are making a true step change in industry. The problem is that graph neural network platforms are very hard to build. And right now, this has only been kind of reserved, or only a few companies, only a few organizations were able to build industry-grade graph neural platforms. So what we did at Kumo is that we built a graph neural network platform that allows you very easily to directly connect to your data warehouse relational data, specify the machine learning task, and get out a predictive model, a solution that is optimized for that given task. So Kumo allows you to basically build graphs directly out of raw tabular data that sits in the data warehouse, allows you to train task-specific private models for a variety of different tasks, get state-of-the-art accuracy, and don't need to do any feature engineering or any training data set generation. All this end-to-end is graph neural network powered, which also means that these models can be put in production and deployed in a matter of days, rather than 9 months, 6 months, that what it takes to put a traditional machine learning feature engineering-based pipeline into production. How does Kumo work? In Kumo, we take your raw relational data here on the left, and we represent it automatically as a heterogeneous hypergraph. Now that we have this heterogeneous hypergraph representation where every entity from every of these tables represents a node, so you could say we have product node, we have user nodes, we have stores, we have customers, we have transactions, we have products. We make this representation automatic. So you as a user don't even need to worry about how do you create the graph, where do you store the graph, how do you represent it. Then we have a task or a problem specification language that allows you to very quickly specify what is the predictive problem you want to be solving, what is the AI problem you want to be solving. So maybe if you are building, let's say, a churn model for your customers, you would say predict count of transactions in the next 30 days. Is that going to be equal to 0? And I'm making this prediction for every customer ID entity in my graph, right? So out of this, Kumo is going to do like a sliding window over your data and understand how does past behavior of the customer predict whether they're going to buy 0 items in the next 30 days. So it's going to attach labels to, in this case, customer nodes, because this is about customer entities, a churn label for a person who perhaps doesn't buy anything in the next 30 days, and an active customer label because they stay engaged and buy things in the next 30 days. Based on this, a graph neural network is then going to be trained, where the graph neural network doesn't even only consider the properties of the target person, but also considers the properties of its neighbors or her neighbors. This is the transaction, store, and a product. And then, of course, each of these nodes has further neighbors. And now we can think of this as almost like a feed-forward neural network that takes all this property information of different entities, learns how to aggregate and combine all this information to give you the optimal prediction that you specified. So Kumo is an end-to-end graph neural network platform where you bring in your relational data. Kumo automatically creates the graph, has its own machine learning optimized database, graph database for quick subsampling of graphs. You have the task specification language that automatically creates a training data set for you. And then you can basically try out all kinds of different architectures and all kinds of different learning strategies to be able to train your models. Why is this so hard? This is hard because you need to take billions of rows and columns in your tables, represent this in a graph, and do all this computation fast enough to keep the GPUs busy. And building a heterogeneous kind of distributed system that can do that is no easy thing. And of course, PyG is great, but PyG only kind of takes care of this last arrow here, and everything else to put in production and scale needs to be built. To give you examples of how Kumo customers are able to use the power of GNNs, here is an example from a large US bank where they want to predict the events of the user in the next 90 days. So this would be the next best action type problem that people solve in history, in industry. The point here being that in a single day, the organization was able to build a model that was as accurate as their internal model that was feature engineered over many years. 3 days later, with more fine-tuning and architectural improvements, they got 76% boost in accuracy of their model, right? So just 4 days from beginning to getting a much more accurate model. Here's another example from a large food delivery business here in US, actually the largest one, where you order food from restaurants using this app. We were doing the try something new recommendations for them, which basically means that we want to predict what new restaurants a user is going to order from. This is over 200 million people because that's the number of customers, and it's a core use case for this organization. Interestingly, Kumo recommendations were 30% more accurate than their internal model. And it's interesting because LinkedIn, in the paper I mentioned, also is reporting a 30% offline lift in recommendation quality. So it seems that GNNs, universally are leading to 20-30% lift in recommendation quality. We actually did an A/B test. Turned out that this led to nearly 150 million of additional revenue for this company just from more accurate recommendations. So these recommendations are extremely valuable. And actually, in terms of hardware spent, this was not expensive. It was actually cheaper than what their internal recommender system was able to do, and how much it cost in terms of hardware. So it's actually cheaper, faster, and much better. The third use case I want to talk about is fraud detection. Fraud detection is naturally a graph-based problem. This is an example from a large bank in United Kingdom, where in 2 weeks, GNNs improved 45% over the internal fraud detection model in this bank. The particular fraud model that we are talking about is money muling, which is a specific type of fraud. The improvement was 45%. And the last example I want to show is that Kumo doesn't only work on humongous data sets, but also works on smaller data sets. Here is an example of a marketing use case where leads are coming to an internal marketing team, and the marketing team is trying to decide which of these leads to engage with and which ones not. And the idea is that you want to engage with a lead that you get if it's going to convert into a meeting and potentially a contract later. So using a very simple model specification, basically they said we want to predict whether a given lead will result in scheduling a meeting and in the next 30 days. A random conversion rate here is about 1%, so only about 1% of the leads that this company gets in is able to convert into a meeting. A third-party tool is about, I think, 4 to 5% conversion rate, so better than random. Kumo conversion rate was I think 24%, right? So much bigger boost in the quality of prioritization of what leads to engage with. And this is a relatively small data set. It's not hundreds of millions of leads, but it's order of thousands of leads. So the GNN technology is extremely versatile. It can be applied on huge graphs and also on relatively small ones. To conclude my part, I will really emphasize that Kumo embraces open source, and we are very excited about scalable abstractions in PyG to enable distributed training, which is the topic of today's webinar. We are also very excited to release what we call PyTorch Frame, which is a multi-model tabular encoding framework to encode tabular data. And then another exciting thing is that we are also releasing what we call RelBench, which is a relational deep learning benchmark. So a benchmark where basically we give very interesting multimodal data sets with very diverse prediction tasks and show how graph neural networks can solve this. In terms of scalability, Kumo is a platform that can process terabytes of raw data, tens of billions of nodes, and tens of billions of edges. So with this, I'm going to finish, and now I'm going to hand it off to Matthias, who will talk more about exciting development in the PyG ecosystem. Thank you so much, and Matthias, please take it away.
Yeah, thank you, Jure. Let me take over. Hope you can see my screen. And today, I'm super excited to talk about the new PyG 2.5 release, which is a pretty big release consisting of over 360 commits from over 40 different contributors. So thank you all for your help in making this release possible. I don't want to go too much into distributed training capabilities we added to the new PyG release, so we will have 2 more presentations later on that go over that in more detail. But I quickly want to highlight the other highlights we had integrated into this new release. And as always, PyG 2.5 supports the latest PyTorch version, which is PyTorch 2.2 at this point in time. But importantly, if you don't want to upgrade your PyTorch, the new PyG release still supports all the PyTorch versions up to version 1.11. And so there are 3 big highlights to announce here, despite distributed training. And the first one is the support for a dedicated graph tensor layout. We added support for recommender systems, and we now have support for native compilation in PyG, and in particular within its message passing interface. So let's dive right into. And so Regarding graph tensor layouts, previously PyG focused on supporting a diverse range of different graph tensor representations. So we started with this edge index representation, which is like a COO tensor of shape 2 times the number of edges. And to me, this is always like a super useful format to have because it's in particular easy to use. So it's easy to modify, easy to understand, and so on. And in addition, it has like a native mapping of indices to its corresponding edge features. So the index of this particular edge directly maps to the index of a particular feature. The downside of that is that the COO format is not necessarily the best if you think about message passing use cases, in particular because conversion to CSR and CSC is quite expensive. Based on that observation, we then introduced the sparse tensor representation, which is like a matrix, a sparse matrix built in COO, CSR, and CSE support, but it also introduced like an external dependency. And in particular, sparse tensor was designed to be always required to be sorted internally. And so if you pass in the sparse indices to a sparse tensor, then you would need to make sure that you also permute the edge features accordingly to this internal reordering. And that makes it quite hard to deal with. And lastly, we then also added support for native PyTorch sparse matrices. And so the main benefit is here that we get rid of this external dependency. But the downside of PyTorch sparse matrices is that they only support a single format, and then you have to convert to a different format, such as CSC, if you need that. And as a result of that, we see like a slow backward pass, because if we use like a sparse matrix multiplication, then the backward pass would need the transpose of the sparse matrix, and that is just inherently slow to compute if you don't have that information before model execution. And then the overarching question here is, which layout should I actually pick? And so with PyG 2.5, we are trying to unify all these different concepts by keeping the best of all worlds. And our solution to that is known as the edge index class. And so edge index is just a regular PyTorch tensor attached with additional metadata. And so we preserve here the ease of use of regular COO workflows. And that means that we also keep this clear mapping of indices to features. But then we also added support in edge index for fast CSR and CSC conversion. And so in essence, that means we have an optimal, or we aim to have an optimal graph representation for message passing without any external dependency, and that is also fully backward compatible. And so you can see on the right how that looks like. So you can just swap out like a torch tensor creation of edge index with like an edge index creation, and then you have access to the additional metadata. So you can store the underlying sparse matrix size. You can clearly denote whether that edge index, for example, is sorted and whether that is undirected. And so implementation-wise, edge index just subclasses PyTorch tensor and extends it by this additional metadata. It also maintains caches for fast CSC and CSR conversion. So if we know that an edge index is sorted, then we can compute the CSR and CSE representations and also cache them over different GNN layers. And that means that within a single GNN model, we only have to compute this representation once and then can reuse it for later uses. Importantly, edge index behaves like a regular PyTorch tensor, but then also preserves metadata over its lifespan. And that means that whenever you make modifications to that edge index, it preserves as much information as it can. So for example, we can directly call the method torch flip on this edge index, which basically flips like the source and destination nodes. which is equivalent to having like a transpose operation on the sparse matrix. And that means that if we have an edge index that was previously sorted by row, it is now sorted by column, and it is still undirected. We can also use like filtering and all the fancy tools that PyTorch provides on tensor data. And so if we have a mask and filter out certain edges with this mask, that means that it's still guaranteed, that the result is still guaranteed to be sorted, but it's no longer guaranteed to be undirected. And so with that, we can directly use edge index as a drop-in replacement for our previous format, but we can still have the benefits of an optimal message passing flow. And that means that we have access to graph modifications as usual, but then we also have access to fast CSR and CSE conversions cached over subsequent GNN layers. Importantly, we added this notion of an undirected graph here because that proves to be super useful if you think about backward passes, because if you have an undirected graph, you can simply avoid calling the transpose here in the backward pass at all. Just to share a quick sneak peek on how that is implemented. And for more information, there's a whole PyTorch tutorial on that. I just thought it's like super cool to share here because PyTorch now provides a super clear way on how to inherit from a PyTorch tensor. And so you could see here in this example that edge index now really inherits from a tensor class. And then all the different functionality and how different PyTorch functions are overwritten is handled by this torch function method. And that means that all different PyTorch functions, when you call them, will go through this single entry point here. And then if you have a specific function that you want to override, you can simply call that inside this torch function, or you can just fall back to a default PyTorch function. So whenever we have a function such as torch flip, for which we want to preserve metadata, we would implement that as part of a function we want to override. And for all other functions such as, I don't know, get index select or whatever, we would just fall back to the original PyTorch function. So edge index is in beta stage, so feel free to try it out and let us know your feedback on that. I'm very curious to learn. And what is planned next? So we want to make edge index a more central concept in PyG overall, deprecating all other different formats. And that means that we want to add more optimizations in message passing for it. Datasets in PyG will now create edge index out of the box with correct metadata set. And then all the functions and transform we provide should preserve the edge index layout as best as they can. With this, I want to share the second highlight on the release, which is like the recommender system support. And so previously in PyG, all link prediction models were evaluated using binary classification metrics, which is, I would say, impractical since it always requires a candidate set in advance. And that means that whenever you don't have a candidate set, you're basically lost here, because the main question is, how can we find the top k most likely links from the full set of pairs? Importantly, there exists a pretty elegant pipeline to solve that. And so the pipeline looks as follows. So you generate the source node embeddings as the destination node embeddings coming from a GNN, and you cache them together. And then you can do KNN search, or MIPS, which stands for maximum inner product search, to find the top k most likely links between source and destination nodes. And then you can evaluate the quality of your model using retrieval metrics such as precision at k, recall at k, and so on. And so in PyG 2.4, we added full support for recommender system based on this specific pipeline. And that means that PyG adds KNN search functionality based on the face library, and it provides support for retrieval metrics that are implemented in such a way that you can just run the metric computation within mini batches and then accumulate the computation over batches. Two more things to highlight. One, we added temporal link prediction support using edge-level temporal sampling, and we provide a fully fledged out example to get you started on that. And so the main flow of the previous slide now looks in code as follows. So we initialize our MIPS index. We iterate over the destination nodes, compute their embeddings using a GNN, and then add these embeddings to our MIPS index. Afterwards, we now iterate over our source loader in order to compute the source embeddings of our model. And then we can use this predefined MIPS index to search the top k most likely links between source and destination. If we have these, we can now iterate over our retrieval metrics and update them accordingly. That means we put in our prediction, which is like a pred index matrix, so a matrix containing the top k indices of the destination nodes for every source node. And then we have the ground truth, which is here denoted as edge label index. And afterwards, we can just call metric compute after mini batching is done. Importantly, we have successfully applied the scheme in Kumo to perform recommendations to over 200 million users across 10 million different products, and it worked pretty well for us, so feel free to try it out. And the last thing I want to talk about is compilation, and that means that PyG introduces basically a full re-implementation of its message passing interface with the goal of being fully backward compatible. In particular, that means that message passing with this new re-implementation is now natively applicable to torch compile and torch script. And so there no longer exist any hacks to make torch script or torch compile work in PyG, so we no longer need to maintain our own methods for that, and instead we can simply rely on the functionality coming from vanilla PyTorch. And in the Kumo case, model compilation leads to up to 3 times faster GNNs, so I'm very curious to learn about your use cases and how you were able to speed up your model with torch compile. Importantly, besides all that features, we were also involved in new libraries that extend PyG. And so we officially released PyTorch Frame at the end of last year, which is like a deep learning library over data frames with support for multimodal data. And that means that you can use PyTorch Frame to encode or learn a representation on tabular data, and then use that representation downstream as input into a GNN. And so you can effectively use PyG now in order to learn over heterogeneous tabular data. We have a fully open source implementation of what we call relational deep learning, which implements this scheme, and that is available on GitHub, and we also have a paper on that on arXiv. With that, I'm happy to pass it over to Kinga to learn more about distributed training in PyG.
Okay, so I hope you can see my the PowerPoint slideshow as well. Okay, maybe I will turn on the camera as well. Okay, so hello everyone. We are honored that we could be here today and present our solution to a broader audience. Maybe I will introduce myself. I am Kinga Gajdamowicz, and I am AI software engineer from Intel Poland team. And together with Jakub, we would like to present to you today our solution for distributed training for PyG that we worked on together with Homing, Kashuan, and Raymond. Yeah, maybe at the beginning I shortly explain what distributed training is and what are the parallelization strategies and which one do we follow in our solution. So distributed training is a method of training machine learning models using multiple computing resources, such as, for example, CPUs or GPUs. And there are, and basically distributed training aims to parallelize the training process across those multiple computing units. And there are three main approaches to distributed training that are data parallel, model parallel, or hybrid approach, which is a combination of those two. And in our solution, we follow data parallel strategy that you can see on the slide when we have a graph that is partitioned, and in general, one partition goes to one machine. And we have a model that is replicated, or we can say it's shared across the machine, because the models of the parameters of the model are shared between those machines. And there is also one important thing to mention here that is specific for GNNs, that because in GNNs we have a graph that is partitioned. And because of the fact that one partition goes to one machine, this machine has access only to some part of the data. And because of that, the sampling process is more complex in a distributed solution. Because we can have, for example, a situation when we will sample a node that is from different partition, and then we don't have information about its features. Or we can have a situation when a seed node is from different partition, and in such a situation we don't have information about its neighbors. And that's why there needs to be an additional communication channel in samplers to handle those situations. And I will discuss it more in details later on. In order to partition the graph, we use the Matthias algorithm, which partitions the graph such that it balances the number of nodes between partitions, and also it minimizes the number of edges between partitions to reduce interpartition communication. And in general, one node is assigned to one partition, but there can be a situation that nodes of different partitions are connected to each other, and these nodes are called halo nodes, and connectivities between them are saved in both partitions, but only connectivities, not features of both. We also provided distributed data storage. Oh, sorry about the light. Okay. We also provided distributed data storage, local graph store and local feature store. And local graph store is a container for graph topology information, and local feature store stores node and edge level features. And these classes have useful methods to create its objects from either data or heterodata, or directly from generated partition. And as the name says, these local graph store and local feature store instances are local, and each machine stores its own instances of local graph store and local feature store. So they consist of information about the only about the partition, not about the whole graph. Okay. On this slide, you can see how the architecture looks like. It works in so-called worker mode, where each computational unit serves as an equal member in a training process. And basically, each machine runs identical training script. And the workflow is that this loader loads data and spawns multiple sampler processes, where each of them takes their own seed. And after the sampling, samplers put their outputs in a torch MPQ. Then this loader takes those data and converts it to the PyG data or data format. And with this data, we can start training the model. On the yellow, you can see there is an RPC group, which is used in two situations. First situation is remote sampling that I will discuss later on. And there is also, it is also used during remote node or edge feature lookup. Because we can have situation when we sampled node that was from the remote partition, and to obtain its features, the local machine must send RPC request to that machine to obtain its features. And there is also a DDP group that is used during model training. Because as I already told you, we follow data parallel strategy where data is partitioned and model is replicated across the machines. And because of that, some mechanism is needed to handle gradient synchronization as well as model parameters synchronization. And it is being done using PyTorch DDP. We also support asynchronous processing based on Python asyncio library and torch features. Among the others, to handling these RPC calls. We also provided distributed data loaders that are used to manage sampler processes, and they are seamlessly integrated with PyG main data loaders like link neighbor loader or neighbor loader. And about data loading, we also provided distributed neighbor sampler that supports different sampling strategies like node or edge sampling, homogeneous or heterogeneous graph sampling, and also temporal or static sampling. And just recently, our colleague also enabled biased sampling. Okay, now I will talk about the remote sampling and overall about distributed neighbor sampler algorithm using this simple example. Because overall, these distributed samplers should return the same output as a single machine sampler in a normal case. But in here, we have a distributed case, and the data is partitioned. And basically, machine has only access to some part of the data. And because of that, the whole sampling process is much more difficult than on single machine case. And we needed to introduce some additional mechanism to achieve correct results. And I would like to explain this to you on this example, using this example. So we have a graph on the top right corner, which is already partitioned, and nodes from 0 to 4 lies on machine 1, and nodes from 5 to 9 lies on machine 2. And we have a seed with 2 nodes, 1 and 5, and num neighbors is equal to -1, which means that we want to sample all one-hop neighbors of the seed nodes. And let's assume that we want to we perform the training on machine 1, which is local, and machine 2 is the remote one. So we started the training, and first we need to check whether the seed nodes are located on remote or on local machine. And we see that node number 1 is from local, so we sample its neighbors on local machine, so it will be 3 and 9. And then we see that 5 is from a remote, so the local machine must initiate an RPC request to the remote machine to perform sampling, because it has information about its neighbors. And remote machine sampled 4, 6, and 9. And then after the sampling, it returns this output back to the local machine. And if all nodes were sampled in a current layer, the local machine merge outputs from all machines and rearrange them according to the sampling order, which is needed for further algorithms to make work, like, for example, trim to layer optimization. Yeah, and our order will be that seed nodes will come first, is 1 and 5, and then the sampled neighbors. Oh, let me. Oh, okay. Sorry about that. And yeah, what we also need to do is we need to remove duplicates because we don't need them. And we see that node 9 was sampled twice, so we just remove the last occurrence of it. And our output nodes will be like this. Yeah, and if we would like to sample the next layer, which is not our case, but if, then we need to obtain new input nodes for a subsequent layer. That will be nodes starting from 3, 9, 4, and 6, because they were just sampled neighbors. And we go back to bullet number 1. But if not, if we sampled all layers, then we collect local and remote node and edge features, remote using RPC, and then we send results to the message channel, which is a torch MPQ. And this is all I wanted to say about the architecture. Maybe let's shortly say something about the key advantages, because distributed training can, among the others, it can significantly reduce the training time because of the parallelization. And scalability means that as the number of machines increases, the time spent on training decreases. And also, distributed training enables efficient utilization of available hardware resources, such as distributed computing clusters, for example. And also, it allows to handle large-scale graphs that cannot fit into the memory of a single device by partitioning the graph. And here you can see our performance results for OGBN products dataset and GraphSage model on Intel CPU. And as you can see, as the more partitions we have, the better performance we can achieve. Maybe important thing to mention is that currently our solution supports only distributed training on the CPU. And I really recommend you to read the tutorial that we prepared, which is available on PyG docs under tutorials in here. And now we can move to the most interesting part, which is a live demo and walkthrough. So thank you very much for listening, and Jakub, you can go on.
All right, thanks, Kinga. Thanks for the beautiful presentation. Let me share my screen. I hope that works right now. Yeah, okay, yes. Here we go. So, hello everyone, once again. Welcome to the demonstration part of the new PyG distributed framework. My name is Jakub Pietrak. I'm also a software engineer at Intel Poland. And today I would like to show you how to use and develop your own distributed workloads with the newly released features for the graph neural networks distributed training. The demo is rather high level. The main aim is to familiarize you with the new distributed functions and classes. We'll go together through a training script. And basically, it's to give you all a head start into development with distributed PyG. I will also give you some instruction on how to set up a simple development cluster, how to prepare and partition your data, how to run a training script inside of your developer's environment, such as VS Code, and finally how to deploy a workload using a customized land script provided with the library. So without further ado, let's go into the setup part. I think the font should be larger right now. Yeah, okay. So for the setup part, assuming you're setting up a new cluster, the most important part is to configure a passwordless SSH connection between all of the nodes participating in the cluster. To do that, you need to generate pairs of RSA keys and then copy them to each member of the cluster. And you have to do it on each node participating in the cluster. After you do that, you should be able to SSH to any of the nodes without being asked for a password. And this is basically what we want. Second part to remember is that you'll need to enable TCP/IP communication through at least 3 different ports. Later, I will explain why we need those 3 ports. So you might need to configure your firewall. For example, if you're using Ubuntu, you might need to check your firewall settings here. Another good advice in here would be to keep the same folder structure at each node, especially when using the land script. You'll need to provide directories to the data folders and to your scripts. And those land scripts don't differentiate between different paths by default. You could use Docker containers for this, but for simplicity of this tutorial, we'll assume that you have basically 3 or you have a number of nodes configured in the same way. So that's pretty much, I guess, the most important parts about the cluster setup. After you have done this, we can start with the data preparations. So basically, to partition your data, you can use one of the scripts that is also included in PyG library right now, the partition graph py, which runs the Matthias algorithm on your data set. I'm not going to run it right now, but we're going to see the output later. An important notice here is that the output of Matthias is not deterministic. So if you run this script multiple times, you're not guaranteed to get the same answer. And when you're running in a distributed training, all of the nodes have to see the same data. So basically, you need to run this at one of your nodes that is capable of handling the whole data set in memory, and then copy the partitions to respective nodes. Alternatively, you could also use shared volume if you have an access to this kind of setup. So maybe now let's see what would you get as an output when you run this kind of partitioning script here. I have previously generated some partitions for 2, 3, and 4 nodes. They all follow the same folder structure. So basically, in each of those partitions folder, you will find this kind of folder structure. The dataset is divided into standard test, train, and validation splits, and we save all of the information into .pt files that can be loaded into PyTorch. So inside those split folders, you'll find partition .pt files with partition index, and basically each one of those files contains seed indices for the nodes that will be later consumed by the data loader. Then in the main partition folder, we have edge map and node map files. Those files contain tensors which assign a partition index to each edge or node in the dataset. Those files will be later consumed by the local graph store and the local feature store, such that when we perform sampling, the data stores know which node to call for the specific node or edge. There is also a metadata file which contains some additional information, such as if the graph is homogeneous or heterogeneous, is the data sorted, and so on. This is especially useful when we're running on heterogeneous graphs. Okay, further in those files, you will find edge features, node features, and the graph PT file, which basically contains information about edge indices in the graph, the whole graph topology, you might want to say. So yeah, basically, whenever you create a partition, you should expect similar output. Also, there are labels. In that case, there are node labels. We'll be running on the OGB products homogeneous graph. Assuming you have your data partition and shared between the nodes, you can start running the script. Today, we'll be analyzing the node OGB CPU.py file. This is a script that performs training of a GNN for a node classification. First, I would like to give you a brief walkthrough through the most important, through the input that you have to provide to this script. And later we're gonna run the training. And when the training is running, I'll explain the most important steps that are happening inside of the main training function. So about the inputs for the end-to-end scripts, in the here we can see that you have to provide those 3 TCP ports. Why 3 ports, you might ask? First, you'll need a port for the DDP data parallel model training group. That's one separate port. And then you'll need a separate port for each loader, because we'll be performing both training and testing. In this example, we're going to initialize a train loader and a test loader. And because each of those distributed loaders is handling RPC communications internally, we need to provide a TCP port for it. So yeah, we have those 3 TCP ports. Then we have the master address. This is the IP address of the master node that we'll be using. In my case, this is the node that I'm presenting on right now. Then we have a flag for asynchronous processing. Basically what Kinga discussed there. I would generally advise to keep this feature on when you're running workloads. However, it might be useful for debugging to turn off the synchronous processing of the RPC requests because the debugging would be a little bit easier then. Then we have the number of concurrent threads that each sampler can launch for processing the RPC requests. Then we have the number of threads assigned to each sampler, and this is a little bit of a performance improvement here because by default, PyTorch, sorry, I'll turn on some light as well, it's getting dark in here. So basically, by default, PyTorch uses a single thread for each sampler, but especially in distributed case, each sampler has, you could say, more work to do. So basically, multi-threading is a very useful feature to turn on. And we use it by enabling this context manager for the data loader. This is where you can control the number of threads for each sampler. Then we have pretty standard arguments. So the amount of workers of the data loader, so the amount of samplers, batch size, number of epochs, node rank, so rank of each node in the cluster, where 0 is reserved for the master node. Number of nodes sampled at each layer of the GNN, size of the cluster, and the directories to your dataset. So this is basically a brief description of all of the inputs. We can now run the training script. I'm basically just running a Python debugger inside of the VS Code here, and I have another VS Code instance opened in another window. I'm doing the same there, and we should see briefly that the training is starting. It usually takes a few seconds to connect. While this is happening, I can talk over the most important parts of the script. So as you can see, the DDP group has connected. Now the loader is starting the sampler processes. and the training should start briefly. So while this is happening, maybe let me just zoom out a little bit. While this is happening, we can talk over the most important parts of the main function of the script. So first of all, we need to load our partition files into PyTorch, into the memory. We load the train and test partition indices. Here, as you can see, I limited the data set to just a few batches to show you a complete epoch iterations in the demo. Then we use this directory to the main partition folder to load it into our local graph store, and using the from partition function, we initialize local graph store and the feature stores. Then we need to create this partition data tuple that will be passed to the loaders. We initialize the distributed context, which basically serves as a container for the information about our distributed setup, the size of the cluster, node rank, and so on. We specify the device that we'll be running to. In that case, it's CPU. Then we initialize the process group using torch distributed package. For CPU, it's advised to use the GLO backend, and we use TCP for initialization method. Then we can initialize our loaders, the train loader and the test loader. Basically, you can see that most of those inputs that we discussed in the beginning are passed to the loaders here. Maybe one more interesting feature here to notice is that we are also using this persistent workers feature. That basically, this flag basically means that when the iterator loop exits, the sampler sub-processes will be kept alive, which allows us to save us some time between epochs, and also stabilize the connectivity between all of the samplers, basically remove some possible errors in there. And we have pretty much the same initialization methods for both loaders. Then we define our base model. We enable the model inside of the distributed data parallel framework. Then we initialize the optimizer. And basically, this is where the standard training loop is already starting. Another maybe good tip in here is that you have to initialize your optimizer after you initialize the DDP. Otherwise, you may run into issues. And in the meantime, you can see the output of the training loop. As you could see, we have run 10 epochs with just 5 batches each. The training has finished and closed. And that's basically what we wanted to see. So basically, this kind of setup is very useful if you want to develop your own scripts, because we don't need any external libraries or tools to run the distributed training here. You can basically set breakpoints wherever you want to and investigate what's going on. Because the DDP works in a way that it has to synchronize all of the models at every batch. If you break the execution on one node, all of the other nodes should wait for this node to finish. This is very useful for debugging. However, if you want to later deploy your workload in more of a production setup and use more nodes, it would be quite inconvenient to handle all of the consoles or all of the VS Code instances separately. So we also provide this LAN script that is basically capable of executing remote SSH commands on each of the nodes that is participating in the cluster, and you can basically control execution just on one single master node. You can run the LAN script directly from the console, or you can use a shell wrapper that is also deployed and it's available in PyG library, and I'll give you a brief walkthrough through this script. So basically, to use the launchpy and the shell wrapper, first thing you need to configure is an additional file called ipconfig, where you specify IP addresses of the nodes that are taking part in distributed training. If you want to extend the list, the cluster, all you need to do is just basically add more addresses here. It's as simple as that. The master node should go on the first line, and basically that's it. Then using the shell wrapper, what we want to do, what we want to achieve in here is basically to compose this command that will be executed through SSH at each of the nodes. So you have to obviously provide the directory to the script that will be executing, and especially if you're running inside of the Anaconda environment, you need to provide a directory to Python execution file. Then you compose the command that will be sent to each of the nodes. We can specify the number of nodes here, specify the directory to data partitions, all other inputs to your training script. And then basically all you need to do is run this in a shell. And the LAN script should launch the training script on all other nodes. Some other nice additional features of this are that the LAN script also takes care of termination of all of the remote processes at remote nodes. So if you prematurely terminate the script, or if the training loop finishes, it will also kill all of the other Python processes, leaving no processes hanging. So we can't really see the full console output here, but to confirm that our training is working, we can look into one of the log files being created. Sorry, I have to exit we have seen already some output, but basically you can also look into one of the log files here to confirm that your training is working as expected. And yeah, that's a very handy way to deploy on multiple nodes. We can also test here if we can terminate the script smoothly. So if I just now break the execution, we should see in the terminal that it's also destroying all of the other processes. And yeah, that basically concludes this brief demo. I hope it will be now easier for you to use the distributed framework. I hope the material presented here was clear enough, and I encourage you to take it for a spin yourself. And with that, I want to thank you for your attention. I think we can give the floor back to Matthias. We can still take some questions.